All right, we showed how you could use a current through one coil to induce a current through another coil. Let's talk about how putting a changing current through a coil or through any conductor can induce a voltage in that conductor itself. And let's take an example similar to the one we did a minute ago. Let's have a battery connected through a switch to a single coil. Like that. And we're going to assume this coil is a long coil so that the B field is equal to mu 0 times the number of turns per unit in length, little l, times the current through it. And we're going to measure the voltage across that coil right there with a voltmeter. So when we close the switch, we produce a current going through here. And if that current will produce a field, and if the field is changing, it's going to change the magnetic flux that goes through the coil itself. And that will produce an EMF that's measured on this voltmeter. So let's see, the EMF, which we will measure on the voltmeter, will be equal to minus the change in flux, the magnetic flux, through the coil. And that's going to be equal to minus d dt times the area of the coil times the magnetic field inside the coil times the number of turns. Okay, that's magnetic flux. So N is just the number of turns and A is the cross-sectional area of the coil. Those are geometry factors. The only thing that's going to change with time is B, and B is going to be that the field that the coil produces itself, this mu 0 N over Li. So we can rewrite this as the EMF is equal to A times N times mu 0 times N over L times di dt. And there's a minus sign in there we don't want to forget. And that gives me then the EMF is equal to minus the area of the coil times N squared over the length of the coil times mu 0 times di dt. All right, so all the geometry of the coil is here, and here's the changing current with time. And we define this quantity here to be equal to L. That's the self-inductance of the coil. That's also measured in henries. So we can then write that the EMF is equal to minus L di dt. All right, what does the minus sign tell you? The minus sign is Lenz's law. That tells you that the EMF is going to oppose the motion of, oppose the change in the direction of the current. And so in this case, if we close the switch and the current is starting to increase, there's going to be an EMF induced that's going to oppose that current. And the way you would do that would be to have this act like this is the plus end and this is the minus end, and we'd have a potential difference that goes across against the direction that the current would normally flow. And so that is in addition to the potential drop due to the IR loss, the resistive loss in that wire. Okay. Okay, let's do an example of mutual inductance. Suppose I have my two coils, and I'm going to draw them separate now, but they're really laying over each other. Okay. Let's suppose we have a case where with this coil, N1 has 300 turns, and this coil over here, N2, has 1,000 turns. Let's make the diameters of both equal to 0.1 meters, and they both have the same length. L is equal to 0.1 meters. And let's suppose that the current is changing at a rate of 20 amperes a second. That's the current through the first coil. So if that current changes, that causes a magnetic field, it causes a changing magnetic flux through that coil, that's going to induce an EMF. Okay? The mutual inductance between the two coils is going to be equal to mu0 times N1 times N2 times the cross-sectional area over the length. That's equal to 4 pi times 10 to the minus 7 times 300 times 1,000. And the area is pi over 4 times 0.1 meter squared. And that's divided by a length of 0.1 meters. And I get that M12 is equal to 0.03 henries. Okay, that's a kind of normal number for inductances, 0.03 henries. They're not it's not like picofarads. It's more like reasonable numbers on the order of 1 or 1,000th or 100. The EMF that's induced in the second coil is equal to minus M12 times dI dt. So that should be equal to minus 0.03 henries times 20 amps per second. And that should be equal to 0.59 volts.